Hello everyone, happy Tuesday to you. It's not actually Tuesday when I'm recording this, but I'm assuming you're going to be checking it out then. Just want to say that I absolutely miss you all. I wish I could be delivering this to you in a different way, but we are going to absolutely make the best of this. So guys, the distance learning chemistry 30 is definitely going to be different than what we were doing in class. Of course, I'm hoping that you're going to be able to make sense between the podcasts and the notes and the assignment. Everything's definitely been pared down a little, so I highly recommend that you find the new notes that I printed instead of using your old ones. It's going to make a lot more sense from that. Also, I really encourage you to please give me a shout on email. So if you got questions or any comments, and then I can answer you individually. All right, folks, here we go. Now, we're going to focus just on two key concepts this week. The first one is predicting and balancing redox reactions, and the second is writing balanced half reactions. It continues on right from where we were in our previous week in class. This podcast in particular is just going to focus on that initial outcome. Have your notes in front of you. Please reference the ones where I posted a PDF form too that are already filled in, especially if you're having a hard time reading some of what the pen is writing, or if you miss a little bit of something. Remember, you can always pause the podcast too. All right, so first things first is we're going to go through what's called a 5-step method for balancing these, and we'll do some practice with them, of course, too. Now, this 5-step method starts by listing out all the major chemicals in a system. And when I say a system, essentially I'm talking about the question that you're going to get. Something's going to be described of what's happening, and you have to make a list of everything that's there. When it says atoms, for example, we're talking about specific individual atoms like potassium. When it says ions, it's exactly what you'd expect. Maybe you have an iodide ion, right? Usually your ions are going to be aqueous. Molecule could be something like water, right? Lots and lots of options here. Now I want to talk a little bit more about this next one to clarify. This is specific to ionic compounds and strong acids, which have been dissociated. If you remember back, I mentioned this in class, perhaps you've forgotten, strong acids, you don't have to memorize these anymore, but an example of this could be nitric acid, for instance, right? Remember, acids always have the aqueous at the end. If you forget what those strong acids are, have a look at your data booklet. This is page 8. And if you check out page 8, right in this section up here, these are all your strong acids, right? So they're listed there. If you're not sure if an acid is actually going to split up completely or not, well, that's where you go, okay? Now, next step going through this then, just to clarify, and if an ionic compound is going to dissociate, what I'm talking about is something like this. If we have sodium chloride and it's dissolved in water, you have to write this one out when you have the individual species written out as sodium ion and also as chloride ion. It's not going to be present as the ionic compound. Vice versa with that strong acid, like the nitric acid that I was talking about. We're not going to follow modified Arrhenius theory that was introduced to you last year. Instead, we split it more simply for the sake of balancing these things, just into the H plus and into the nitrate ion. Again, guys, I know the pen's a little off. I'm doing my best here, especially with my left-handedness on. So do look at the PDF notes. Everything is on there in my nice, neat writing. It'll be a little easier to see. Okay, last little bit that you have to pay attention to is check if it mentions what sort of conditions are being dealt with. Okay, generally speaking, for everything that we do in class, we're going to do acidic conditions. We leave out basic conditions for the sake of distance learning here. If acidic conditions exist, right? So acidic solution is like acidic conditions. Oh, where'd it go? Hurry up. Sorry, guys. Come on, pen. Work with me. So acidic conditions means that as soon as you see something like that, include H plus as what's being listed. You'll find this comes in really handy when you're trying to pick out which half reaction is an option. All right, let's move on. Okay, Number 2, this goes back to something familiar that we talked about before we were off, the SOA. Now, SOA, if by any chance you've forgotten, stands for our strongest oxidizing agent. And the strongest oxidizing agent is always undergoing not oxidation, and that's that key distinction, but is undergoing reduction. Okay? Remember that those undergo opposites. So SOA undergoes reduction. Leo-Gur, which means it is gaining electrons. Oftentimes, we'll end up with a situation that it's a combination of chemicals. It's not just one chemical individually that's acting as the strongest oxidizing agent. You have to write them all down. Again, I'll show you what I mean in a moment. If you have to identify an SOA, next step naturally is you're going to have to identify an SRA, which once again stands for your strongest reducing agent. Similar type thing, the SRA undergoes oxidation, which means it is the Leo part, it is going to be losing electrons. Step 4. Step 4 is one that should feel familiar. We've done this with electrons already. You have to balance them out. Make sure that what is being gained from an electron perspective is the same as what's being lost. And then we need that net ionic equation. If you think back to what we were doing before, net ionic equations means that there's no spectator ions included. It just has the reactants and the products. Anything that can be canceled out should be canceled out. Just a moment here. This is my palm touching things. Cancel that. There we go. No tater ions. Okay, very last step here is to classify the reaction. We've got two options. It'll either be spontaneous or non-spontaneous. Again, this is something we were talking about right at the end of what we were doing. If a reaction is spontaneous, then the oxidizing agent is going to be listed higher than the reducing agent. Vice versa, if it's non-spontaneous, the oxidizing agent is going to be listed lower than the reducing agent. So if you think back to our charts, and I'll reference one in here in a moment, you have to really think about where they're located to show you if you have a spontaneous reaction or not. Think about this table. This is page 7 of your booklets. And if you have a look at it, if you go right to the top of it, that highest one, fluorine, is considered to be the strongest oxidizing agent on this entire chart. That means then that by the nature of that being the highest oxidizing agent, if we go down to the bottom to lithium, this is going to be our strongest reducing agent of our entire chart. There's lithium. Now, anything on this whole table that ends up being higher from an oxidizing agent than a reducing agent, we have a spontaneous reaction. Vice versa, if the oxidizing agent is lower, we therefore have a non-spontaneous reaction. Keep that in the back of your heads. It'll come back. All right, let's try one of these things. Again, I really recommend that you reference your actual PDF notes that I've posted because it's going to make it a lot easier to follow along. But hopefully the conversation of the podcast will help too. What we got here? A couple key language things. Solution is mentioned and solution is mentioned. If you see solution, that's trying to communicate that water is present. And if water is present, it's going to have to be listed as one of the chemical species that are there. The next things that you see are two different ionic compounds. Now you need to assume that an ionic compound is going to dissociate. That's why they are solutions. So you're going to have to take both of those and split them up, dissociate them into their individual ions. Okay, let's list everything to start. Water, like I said, is going to be there for sure. So H2O liquid. I usually spread these out with a comma. Sodium hypochlorite means that we have sodium ion present. The hypochlorite is that OCl negative. please take notice with all of these ionic compounds that are dissociated. I'm putting aqueous there to show, yeah, these things are in solution. Potassium, the K plus, and iodide, I negative aqueous. We have 5 different things that are present. We're on to the step 2, and honestly, I kind of do 2 and 3 together, where we have to identify the strongest oxidizing agent and the strongest reducing agent. Now remember, sometimes it'll be more than one acting together. This is the point at which you have to start scanning. So if you go back to your table here and have a look at it, we have to hunt, and I usually start with the SOA. So start right at the beginning and start scrolling your way down until you can find something that's on your list there. And I got to it pretty quick here. Here it is. Look at what's there. Both entities are present, okay? So I'm looking first for my oxidizing agent, which means this is a reduction reaction. I've got my hypochlorite there. I've got my water. So both of those are present. They're both allowed. There's my strongest oxidizing agent. So next step with that is to simply write down that exact equation. Usually label it, so be like, okay, this is my reduction reaction, right? SOA is undergoing reduction. And we've got our OCl negative aqueous plus H2O liquid. Don't forget the electrons that are listed there, plus 2 electrons. This is the gain. It's a one-way arrow. That's how this individual is working. Cl negative is produced along with 2 hydroxides. Okay, similar type process when we start to look for our SRA. Start at the very, very bottom and start scanning. Move your way up, see if you can find anything of those. At first glance, this looks like we're in the right spot, but the problem here is if you check it out, we don't have any silver. You can't create things that aren't there. You can't create things that don't exist. So that's not going to work. So keep on going, keep on scrolling, keep scrolling, and bingo, here we go. Just iodide by itself. Remember that this is going to be the SRA, which means it's an oxidation reaction. We have to look at this going this direction. Okay, same process, write it down. This time though, we have oxidation. So we write it the exact same way it's listed, which means you've got 2I negative aqueous that is going to be producing I2 solid and 2 electrons. Step 2 and step 3 are now done. Step 4 is where we start to check this out and see how the balancing the electrons works. Now, sometimes they're already balanced. This has 2 electrons gained, 2 electrons lost. That makes it nice and easy. No big deal. If that's the case, then we're already ready to figure this out as a redox reaction. This is the same as what you were doing before. Add those 2 reactions together. Remember, a redox reaction is the net ionic equation. All species have to be listed. Things are already balanced. So we have our hypochlorite plus H2O liquid plus those 2 iodide ions produces the chloride ion, the 2 hydroxides, and of course, the I2 solid. My electrons are canceled out, so I don't need to include them. One more thing, step 5, is figure out, is this reaction spontaneous or not? Indeed, my OA was absolutely above the RA. So the way we do this is just above the arrow, write that little shorthand, SPONT, spontaneous. You don't have to write the whole word. SPONT works great. Okay. There's one of them done. Let's check out another one. Little bit of a clarification here as we keep on going. Remember that reactions show evidence of change. We've talked about these already. What are the 5 different things that we often see that show reaction has occurred? Stuff like a color change, a gas produced, any sort of a precipitate forming, etc. Now, if we can predict observations based upon the actual equation that we make, we're in pretty good shape. That way, when we do the reaction, it can be confirmed or denied by these observations. I'll show you what I mean. Here's another question. I'm telling you straight out that this one's spontaneous, so you know that you're going to see observations. Now, take note of what's going on. Potassium metal is being, and we've got our other entity, placed in water. This is a very simple reaction, right? The balanced redox reaction, okay, same thing as the net ionic equation, and here's that extra step. Predict the observations this time. Okay, same thing. You're given a scenario, you need to write out all the different entities that are present. This one's a little bit easier in that regard. We have potassium metal, which is K solid, and we're told that it's put in water. So honestly, guys, that's all that's there. The K solid, the H2O liquid. Same process as before. Go to your data booklet and have a look. Start scanning right from the top. And as you scan and scan and scan, and move your way down, you're going to see that as you go through, nothing's been listed yet. Keep going, keep going, keep going. Here, finally, we get to it, where there's some water as a reduction reaction, right? Our SOA. So that's the equation that we need down first. Write it down. This is going to be reduction, and I have my two waters that are gaining 2 electrons and is going to produce my H2 gas plus 2 hydroxides. Now I should note, guys, I usually do this on my own work when I'm going through. I'll make myself a little cheat. So if this water was my SOA, I'll label it as such. Like, okay, that's my SOA. So for example, if you go back to that previous example, if we were taking our hypochlorite with the water, I'd put a square bracket around them and be like, hey, this is my SOA. And then I'd go to my iodine and be like, okay, this is my SRA, just to make sure that things are not confusing when you look back. That means that my potassium must act as my SRA. Do a quick check. Always glance through things. We're going the opposite direction this time. So we start at the bottom. Oh, this happened quick. There's potassium right there. Good news here is, without a doubt, we can see the spontaneity here. My water as the SOA is higher than the potassium as the SRA. All right, oxidation reaction then, because we know that this is my SRA in potassium. We're going to end up with our potassium solid, which is going to then produce K plus aqueous ion and 1 electron. Okay, check out those electrons this time. Things are a little bit different. We have 2 electrons being gained and only 1 electron being lost. This is that scenario where you have to balance them. The previous example, they already were. I can take this oxidation reaction times the entire thing by 2, and we'll end up with a lovely balanced redox reaction. Okay, similar idea. Write it all out. 2 waters plus potassium solid, remember electrons are now cancel out, produces hydrogen gas plus 2 hydroxides plus potassium ion. And don't forget to write that it is spontaneous above the arrow. Last step here for observations. Now, observations, you need to do a couple different things to be able to catch these. Definitely look at the products, because that's going to be a huge hint of what you see. But don't forget to glance at the reactants too and see what's changed. I'll go through each of these individually. So for example, we have H2 gas being produced. So you need to make note of that. One of the observations we'll see is definitely going to be bubbles up gas. We also have a situation where hydroxide is being produced. Hydroxide is a base. So if I end up taking some litmus paper and doing a litmus test, I'm going to see it goes blue because it becomes more basic. The last one that's a little bit less obvious is here. You are going to have a decrease of the potassium solid. right? Because essentially that K solid goes into solution. It's going to become K plus reduced mass of the original solid. There it is. Get in a habit, please, for these questions that you should be writing down possible observations. Look for all of them that you can. All right, let's try another one. Gave you a little picture of what's happening here. In the diagram, if you check it out, what you've got is copper placed in nitric acid. So the copper, of course, is just a penny, but notice the color of the solution here. We're going to talk about that a little bit, right? Think about observations as we do these. Now, first things first is we're taking a solid metal, and then remember what I was saying, solution is important. As soon as you see the language of solution, then you need to recognize that we're going to have some water going in. So step by step, list that one first. It's the easiest one to forget, so I always make sure that I have it right away. H2O is present. Then, of course, we're going to have our copper solid. And nitric acid, okay, nitric acid, check your list of acids. If it's one of the strong ones, which, yeah, it is, then you need to show that it completely splits up into H plus aqueous and NO3 negative aqueous. This is important. If you don't show that splitting, you're going to have a hard time finding the SOA and the SRA in your table. Okay, that's our next step. Check this out, see if we can find them. Starting right at the top, work your way down looking for that SOA. So scroll, 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 keep going, keep going, keep going, and there it is. We've got that nitrate. See what I mean about you had to split it up to see that. And there's the H plus. SOA is officially found. Write it out. If that is your SOA, then that is going to be your reduction reaction. And make note here that it is the combination of those two that is acting as your, oops, not those two. So, sorry guys, I cleared out my entities there. So it's the combination of that H plus aqueous and the NO3 negative aqueous together that is acting as the SOA. Reduction reaction then, we have 2 NO3 negative aqueous plus 4 H plus aqueous plus 2 electrons produces N2O4 gas. And just so you're curious, that's why that color is there. That's the color of that dinitrogen tetraoxide gas. And 2 H2O liquid. Okay, move on. Let's look for what our SRA is going to be. If you remember back, we've got water liquid that's there, and we also have that copper solid. So glance over here. We're starting at the bottom this time, looking for the SRA. Start scrolling, start scrolling, start scrolling, and there's our copper. Between the two, once again, it is above, so we have, as it should be, a spontaneous reaction here, which means observations will be seen. Okay, write it out. Oxidation reaction. Copper solid is going to lose electrons to become copper 2 plus aqueous plus those 2 electrons. Check them out. We have a situation where 2 are going in and 2 are going out, which means everything is already balanced. So when you do your redox equation, it makes it a little bit easier. As we go through this, oh, I just realized when I went through this one, I didn't balance it. Okay, we'll go back to that previous example. Sorry about that. Okay, here's our redox. So 2 NO3 negative aqueous plus our 4H plus aqueous plus copper solid produces that N2O4 gas plus 2 waters liquid plus copper 2 plus aqueous. check out those observations again. Because the 4H plus is being reacted, this whole system is going to become less acidic. You're also going to see, because of the dinitrogen tetraoxide, bubbles of gas produced. And this is something to take note of. Observations are really, really helpful to look at on page 11 of your booklets. So go back to your booklet, and if you check out page 11 on here, stuff like this. Look what we've got. When we have copper 2 plus that gets formed, we see a color change. So the solution becomes blue. Now, that's a good hint because there's our copper 2 plus being formed. So now you know, when you write it out, that we should have that copper solid changes to copper 2 plus, which makes it blue. All right, and there we have it. All right, guys, I meant to go back to this one. Sorry, I realized as I was looking through, I neglected to actually do my increasing. So we times, if you remember back, this equation by 2. So go back in your notes, fix this. That means we're going to have 2 potassium solids formed, and of course, 2 potassium ions as well. Definitely don't forget that. Last little bit here, guys. Here's your homework for this section. You can now do on that weekly assignment, number 1, A through D. Second part of your week's work, I'll do as a separate podcast. Have a good day.